Hey Hank, today I'm going to be presenting for part B on the heuristic algorithms. I'm going to be focusing on genetic algorithms because there's so much material with heuristics that I want to focus on a specific genetic algorithm, which I'm going to do crossover later so I can explain it better. And I'm going to be showing how you can solve traveling salesman problems with the heuristic algorithms, including the genetic algorithms. So going over traveling salesman problem, it's an NP-hard problem, which means NP-complete problems are shown to have polynomial time Turing reducible to an NP-hard problem, which is very confusing, but it basically means that an NP-hard problem has sub-problems that are NP-complete problems. So in order to solve an NP-hard problem, you have to solve multiple NP-complete problems, which means that although NP-complete problems have been proved to be able to be solved in polynomial time, there may be a method of doing that, but for NP-hard problems, we're almost completely sure that there's no way of solving them in polynomial time. So brute force methods for traveling salesmen are very implausible, even for just a few cities. So 20 factorial has 2.432 times 10 to the 18th possible solutions that you would have to go through just to be able to find the most optimal solution. So heuristic algorithms are used as a reasonable answer to solve NP-hard problems in a reasonable amount of time. So heuristics trade accuracy for speed. So it's basically saying that instead of taking so much time to solve this one NP-hard problem, we're going to make an approximation, and usually they come within 2 to 3% for the newer algorithms of the global optimum solution. So the approximations and guesses are made. So it looks for local optimums and solutions that are completely off from the optimums, and throws the ones that are completely away from the optimums out of possible solutions, and then it zooms in on local optimums and does problems related to that. So there are many everyday examples for heuristics, including search queries and antiviruses. So with antiviruses, instead of going through the entire computer looking for a virus and what this virus would look like as a string, it looks for common occurrences where viruses are usually placed inside an operating system and how they usually look, rather than going through the entire operating system and trying to read through every single bit to see if if a virus is inside that operating system, which would obviously take too long. So there are 3 steps in making a heuristic algorithm. First, you have to find the exact solution for a problem. So obviously you can only test this with lower numbers, but obviously with traveling salesman, we found that with the n factorial solution to it of going through all possible steps and then seeing which one gave the global optimum. Then you have to find an algorithm that will give a solution that is close to the global optimum. So within your criteria, so within like the 2 to 3% or like 5% of the global optimum. And then you have to find special cases where very accurate heuristics are possible to test it, and also to investigate those cases. So for TSP problems, there's exact solution. Time complexity is n factorial, which makes it impossible, so we have to use the heuristics. And then it tests every single possible solution, so I've gone over that. So genetic algorithms specifically, they're mirrored after natural selection. So best possible solutions are explored while slower solutions are ignored. So it goes through multiple types of solutions and it looks for the ones that give the best answer. And then the ones that give the best answer, it will focus on that set of solutions for the time and ignore the ones where slower solutions were found. So random mutations are needed for this though. They're thrown in so you don't get stuck around a local optimum. So a local optimum is a set of solutions that is close to the global solution but doesn't reach your criteria, and basically the problem will keep on, or the genetic algorithm will keep on trying to find something that reaches that criteria in that set of solutions, but it never will because there's no solution that's close enough to it since it's only a local optimum, and it will get stuck there looking for a solution that's better and better even though it's not there. So random mutations are thrown in, and random mutations can be inverses or just randomly changed numbers, where if, like, for example, if you have a gene that's 0, 1, you can change that to 1, 0. So that will just inverse it around, and it will throw it away from looking into that local optimum, so it won't get stuck there. So it'll just throw some randomness into the problem, so that way you can get closer to your global optimum. So these operations are performed until some criteria is reached, which is the percentage of how close you are to the global optimum. So crossovers are the simplest ways, or simplest forms of genetic algorithms, especially when you're using just binary numbers. So you test strings of certain length against one another to see how good that number will fare in the problem. And strings with better solutions are more likely to be used in the crossover. So I'm going to go over one of the examples that was used in the senior thesis that you gave us. So this is for maximizing the value of this f of x problem. And I chose two random numbers and I've converted them to binary. So 13 is 1101 and 4 is 0100. And 13 gives us negative 281 and F4 gives us negative 11. So so going over that with the whole randomness and natural selection, you're going to give a higher probability of crossing over, going to the next generation of steps to f of 4, since it gives you a better value, while f of 13 will have a lower probability of making it to that next generation. So the crossover is the next generation, where you take the specific genes and you cross them over with each other of the ones that you've chosen to go over to the next generation. So if I had the 13 and the 4 going over to the next generation, I would cross out with the genes, and then for the 13, that crosses over, so 13 takes the 1 and the 1 from 13, and the 0 and the 0 from 4, and gives you 1100, so that gives you 12. And then for 4, you cross over the 0 and 1 from the 4 and the 0 and the 1 from the 13, and you get 0, 1, 0, 1, which gives you a 5. So 4 again gives you the better answer, so you have a higher probability of crossing that over to the next generation. So hopefully what the problem is trying to do is ignore those higher values. So with the 1, 1 gene, it will most likely get removed very quickly from the possible solutions, because the only problems with the 1, 1 gene later on are like 12, 13, 14, 15. So they're higher and they'll give very low values, very bad values. So most likely all of those will get removed, since they won't have a good value, and that gene will get faded out almost immediately. So you won't have to deal with many of those numbers. So in concluding, we're just trying to get not as many possible solutions, to go through as many possible solutions. And although we only have a range of 0 through 15 for the solution that I was going over, that's if you're taking out, say, the 12, the 13, the 14, the 15 from the problem, that's a quarter of all the answers, the solutions to the problem. And that might not seem a lot for that, but if you're taking something with 20 factorial possible solutions, taking out a quarter of those solutions is very useful in speeding up that algorithm. So there are many more types of genetic algorithms which I haven't had time to go over, since I was focusing on that. There's prisoner's dilemma and parallel imputations in matrix field, but all of them use the same idea of having genes and crossing them over with each other, and then throwing in that randomness so you don't get stuck at local optimums and reach something that is close to the global optimum. Now, going over this, I was only using binary for this example, but there's any type of symbol is possible with this. You just have to make sure you have a set value to that symbol, and there are a limited amount of symbols. So you could use the alphabet, you could use whatever you made up symbols you want, as long as you're giving them a value and you're giving them, there's only a limited amount of them. So that's it. I hope I've explained heuristics and especially genetic algorithms well enough. And thanks, Hank.